Welcome to Year 10 Environmental Science. Chapter 2, Energy Flow and Nutrient Recycling. Energy moves through food chains in one direction, from the sun to producers and then to consumers. While energy is mostly lost from ecosystems as heat, it is constantly replenished by the sun. In contrast, essential nutrients are in limited supply on Earth. Unlike energy, nutrients are not continuously supplied from space. Organisms rely on recycling these vital chemicals and materials. They take in nutrients as food and return waste back into the ecosystem. When an organism dies, decomposers break down its tissues, releasing nutrients back into the environment. These decomposers extract energy for their own growth, breaking down organic molecules and returning chemical nutrients as simpler compounds, thus replenishing the nutrient pool in air, water, and soil. Producers then utilize these nutrients to create new organic material. Elements like carbon, hydrogen, oxygen, nitrogen, and phosphorus cycle through ecosystems, moving from the physical environment, that is air, soil, and water, into organisms and back again. The movement of chemical elements within ecosystems is referred to as biogeochemical cycles. Water and chemicals, such as carbon and nitrogen, primarily cycle through the atmosphere, while others like phosphorus, calcium, potassium, and magnesium circulate mostly in local ecosystems. Lesson 1: Energy Cycles. First, let's talk about carbon cycle. In terrestrial ecosystems, plants absorb carbon dioxide from the air through their leaves during photosynthesis to create organic matter, which accumulates as plant tissue. Aquatic plants and algae perform a similar function by absorbing carbon dioxide or hydrogen carbonate ions dissolved in water. This carbon is then transferred along food chains as organic matter. Carbon is returned to the atmosphere through cellular respiration by animals and decomposers, completing the carbon cycle. While this cycle operates rapidly, some carbon can be stored for millions of years in fossil fuels like coal and oil, formed from the remains of ancient organisms. Natural processes such as erosion, volcanic activity, and fires can release stored carbon back into the atmosphere. The burning of fossil fuels since the Industrial Revolution and deforestation have disrupted the natural carbon balance. In natural ecosystems, there is a balance between the carbon dioxide absorbed by photosynthesis and the carbon dioxide released through respiration. Deforestation has reduced the number of trees available to absorb carbon dioxide, leading to an increase in atmospheric carbon dioxide concentrations since the Industrial Revolution. Measurements of air trapped in polar ice reveal that carbon dioxide levels rose from 270 parts per million before the Industrial Revolution to 345 parts per million in 1984, with projections of reaching 600 parts per million by 2050. Some of this increased carbon dioxide is absorbed by the oceans as hydrogen carbonate ions, benefiting coral reefs. However, the oceans cannot absorb carbon dioxide quickly enough to keep up with rising levels. While higher carbon dioxide levels could enhance photosynthesis, leading to increased plant growth and agricultural yields, they also pose risks for global climate change. Carbon dioxide, along with water vapor and gases like methane, absorbs infrared radiation, which slows the release of heat from the Earth. This process acts like a thermal blanket, helping to keep the planet warm. Without it, Earth's surface temperature would be around -18 degrees. This natural phenomenon, known as the greenhouse effect, is being intensified by rising carbon dioxide levels due to fossil fuel combustion. As a result, average atmospheric temperatures are increasing. Significant releases of methane also contribute to this issue, with nearly half of global methane emissions linked to herbivore digestion and decaying vegetation in rice fields. A temperature increase of 3 to 4 degrees could lead to polar ice melting, rising sea levels, and flooding in low-lying areas. Recent observations indicate that Arctic waters are becoming fresher, signaling the melting of polar ice. Changing weather patterns could lead to drier conditions in regions currently suitable for cereal cultivation, although some argue that current warming trends are part of natural climate fluctuations. Nitrogen is crucial for all organisms as it is essential for protein synthesis, can limit growth, impacting primary productivity in ecosystems. This is why farmers often add nitrogen in the form of nitrate to crops. However, excessive use of nitrogen fertilizers can lead to pollution and health risks, such as illness in infants and potential links to stomach cancer. Excess nitrate can leach from agricultural and forested areas into waterways, and wastewater from sewage treatment plants contains nutrients that must meet regulatory standards before being discharged into rivers or streams. The nitrogen cycle relies heavily on specific bacteria, as plants cannot directly absorb nitrogen gas from the atmosphere. The atmosphere consists of 78% nitrogen, and some soil bacteria can fix this nitrogen into ammonia. Other bacteria convert ammonia into nitrate ions, which plants absorb through their roots to form proteins. Animals obtain nitrogen by consuming plants or other animals. Decomposers return nitrogen to the soil by breaking down organic matter, while denitrifying bacteria release nitrogen gas back into the atmosphere, completing the cycle. For every 23 nitrogen atoms on Earth, there is only one phosphorus atom. Despite this, phosphorus is needed in larger quantities by organisms and is often a limiting factor for plant and animal growth. The phosphorus cycle operates quietly, slowly being released into soil and water through rock weathering. Phosphate dissolves in the soil and is absorbed by plant roots, passing through food chains until it is returned to the ecosystem by decomposers. Phosphorus can also be washed away by runoff, eventually reaching oceans where it can precipitate as marine sediments. Over time, these sediments become compressed into rock, and weathering starts the phosphorus cycle anew. Intensive agricultural practices can deplete available phosphates in the soil, and when crops are harvested, the phosphorus they contain is removed without being naturally returned through decomposition. Water is vital for life, with animal bodies composed of around 95% water. Around 97% of Earth's water is found in oceans, readily available to marine life. Land organisms depend on the cycling of water between the oceans and the atmosphere. Water evaporates from the oceans, travels through the atmosphere, and falls as precipitation, which is rain and snow. Some evaporates again, while a small portion is stored in lakes, glaciers, or underground. Eventually, most of the water runs off the land into rivers and returns to the ocean, completing the water cycle. While this is the overarching cycle, local ecosystems do not experience significant water cycling, as most water quickly evaporates or runs off elsewhere. In urban ecosystems, rainwater often drains into stormwater systems to prevent flooding, but this runoff can carry pollutants, including litter and chemicals. A 1996 study of Port Phillip Bay found that urban stormwater is a major source of pollution in the bay's marine ecosystem. Water is also crucial for food production. In Australia, a dry country, irrigation is often necessary, with approximately 700 liters of water needed to produce 1 kilogram of oven-dried grain from irrigated wheat, while producing 1 kilogram of beef requires around 50,000 liters. Managing Australia's water resources is essential to meet future population needs and prevent water shortages during droughts, as seen in Victoria from 2002 to 2005. Our daily water usage can be surprisingly high. Lesson 2: Water Cycles. As mentioned briefly in the previous lesson, water is crucial for life. Animal bodies consist of around 95% of water. Around 97% of Earth's water is found in the oceans, making it readily accessible to marine life. In contrast, terrestrial organisms rely on the water cycle, which connects the oceans and the atmosphere. Water evaporates from the oceans, moves through the atmosphere over land, and returns as precipitation, like rain or snow. Some of this water evaporates again, while a small portion is stored in large lakes, glaciers, ice caps, or underground. However, most of it ultimately flows off the land into rivers, returning to the ocean and completing the water cycle. This provides a broader perspective. Within this global cycle, local ecosystems do not experience significant water recycling. The amount of water cycled back from organisms to the soil, ponds, or rivers is minimal. Instead, water flows through ecosystems, as most evaporates back into the atmosphere or runs off to other areas. When rain falls on houses, gardens, and streets in urban areas, it flows into downpipes and stormwater drains, which are separate from the sewage system. These drains help prevent flooding by directing water into nearby creeks and bays. However, stormwater often carries pollutants, including litter, leaves, detergents, pesticides, pet waste, and bacteria. A study conducted in Port Phillip Bay found that stormwater from urban areas is a major contributor to many pollutants in the bay's marine ecosystem. Thank you for watching. I hope you've enjoyed the content and have learned something. If you like our videos, check out our other videos on environmental science, and don't forget to subscribe. If you have any feedbacks or suggestions, please put in the comments section.